This is the Brooklyn Bridge. You have seen it countless times, on postcards, in movies, and across social media. But the most remarkable part is not above the water. It is down below, buried beneath the East River. How do you build a bridge across a major waterway when there is no solid ground underneath it? In 1870, the answer almost killed everyone involved. At the time, New York and Brooklyn were separate cities. More than 130,000 people crossed the East River every day by ferry. But the ferries were unreliable. Fog could stop them. Ice could shut them down in winter. Passengers could be stranded on the wrong side of the river for days. So why not build a bridge? There were two major problems. First, the East River was almost 1,600 feet wide. That is more than 4 football fields. Second, it was one of the busiest shipping channels in the world. Engineers could not simply fill the river with supports and turn the waterway into an obstacle course. Only one design seemed capable of solving the problem: a suspension bridge. 2 towers, cables stretched between them, and the shipping channel left open below. But there was a serious problem. In 1870, suspension bridges had a history of collapsing, and the man who claimed he could build the largest one ever attempted was about to become the bridge's first victim. His name was John Roebling, a German-born engineer, 63 years old, and already considered a legend. He had completed several suspension structures across America, but this bridge would be his masterpiece. A span across the East River, more than 50% longer than anything previously attempted. He also wanted to use a material never before used on this scale: steel. Earlier suspension bridges relied mainly on iron cables. Iron was established. Iron was trusted. But for a span this long, Roebling believed iron would fail. His calculations showed that steel had far greater tensile strength. It could hold. In June of 1869, the federal government formally approved the plan. Construction could begin. 3 weeks later, John Roebling was standing at a ferry landing on the Brooklyn waterfront, surveying the place where his bridge would rise. A ferry entered the dock and crushed his foot against the wooden pilings. Doctors amputated several toes. Roebling rejected much of the available medical treatment and attempted to treat the injury himself. The wound became infected. 24 days later, tetanus killed him. He never saw a single stone laid. The bridge had taken its first life before construction even started. It would not be the last. In August of 1869, responsibility passed to Washington Roebling. He was 32 years old, a Civil War veteran and the dead engineer's son. Now, he was leading the largest construction project in American history. Almost immediately, he encountered a problem his father had underestimated. The East River was tidal, salty, and dangerous. Beneath the surface was not solid rock. There were deep layers of mud, clay, sand, and glacial deposits. To support the towers, Washington had to dig through all of it until he found a firm foundation. On the Brooklyn side, workers descended approximately 44 feet. On the Manhattan side, they went nearly 80 feet, and still did not reach bedrock. That was roughly the depth of a 7-story building. Except they were traveling downward, beneath a river. How do you excavate an underwater foundation that deep using 1870s technology? There was no scuba equipment, no modern tunneling machinery, no advanced pumping system. Washington turned to a technology that had only been attempted a handful of times: the pneumatic caisson. A caisson was an enormous chamber placed on the riverbed. It was open at the bottom, sealed at the top, and filled with compressed air to keep the water out. Imagine turning a bowl upside down, then pushing it beneath the surface of a sink. A pocket of air remains trapped inside. Now imagine that bowl is the size of half a football field, built from enormous timber beams, and lowered to the bottom of the East River. That was the caisson. It was either brilliant engineering or complete madness. Workers entered through an iron shaft fitted with an airlock. The pressure increased until it matched the chamber below. Only then could they open the lower hatch and descend into the excavation area. What waited beneath the river was brutal. The air pressure could reach approximately 35 pounds per square inch. The chamber was hot, humid, and dark. Gas lamps hissed and flickered. Workers stripped to the waist. Cold water gathered around their feet as they shoveled mud, removed stones, and broke apart the riverbed. When they encountered large rocks, they used dynamite. Inside a pressurized wooden chamber beneath a river. The workers earned approximately $2 a day. It was slightly more than ordinary laborers received, but nowhere near enough for the danger. Then the real threat appeared. Not in the river, but inside their blood. When workers returned to the surface too quickly, dissolved nitrogen formed bubbles in their bodies. Those bubbles damaged muscles, blocked circulation, and injured the spinal cord. Men emerged suffering severe pain, dizziness, paralysis, and seizures. Some doubled over and could not straighten their backs. The condition became known as caisson disease. Today, it is called decompression sickness. Doctors did not understand the cause. They blamed bad air, exhaustion, and alcohol. They prescribed ginger ale, cold showers, and leeches. None of it worked. The turnover rate was enormous. Some men completed one shift and never returned. The exact number of deaths remains disputed. Official records usually identify at least 20 deaths across the project. The true number of workers killed or permanently injured may have been higher. Then, in 1872, the caisson claimed its most famous victim, Washington Roebling. Washington regularly entered the chambers to inspect the work. During one emergency, he reportedly remained underground for many hours while workers fought a fire. After repeated exposure to high pressure, his health collapsed. He was carried home and never regularly returned to the construction site. At 35 years old, Washington suffered severe pain, impaired vision, and serious neurological damage. For the next 11 years, he supervised construction from a house overlooking the bridge. Using a telescope, he watched the project from a window, the mind behind the bridge trapped inside a body that could no longer reach it. Then his wife stepped forward. Her name was Emily Warren Roebling. She had no formal engineering degree. She held no official position on the project, and she lived in a country where women could not yet vote. But Emily became Washington's eyes, hands, and voice. She carried his instructions to the engineers. She studied mathematics, material strength, cable construction, and structural design. She interpreted his calculations. She met with contractors and officials. And when members of the bridge company considered removing Washington, Emily defended his work and authority. For decades, the official story credited Washington Roebling with completing the Brooklyn Bridge. His name appeared on plaques and in textbooks. Emily was often treated as a footnote. But without her, Washington may have lost control of the project, and the bridge may never have been completed according to the original design. Once the caissons were secured beneath the river, construction began moving upward. The towers had to rise more than 270 feet above the water. At the time, they would stand among the tallest structures in New York. For years, workers lifted enormous granite and limestone blocks using steam-powered cranes, derricks, and pulley systems. Every block had to be positioned with extreme precision. By the middle of 1873, the Brooklyn Tower had reached more than 160 feet. The Manhattan Tower remained far behind. The Manhattan Tower did not reach the same stage until 1876. The work was slow, the conditions were dangerous, and the cost continued to rise. The project had already consumed its original $5 million budget. Additional funding had to be approved before construction could continue. By the end, the total cost would reach approximately $15.5 million. But eventually, the two towers stood above the river. Stone giants anchored deep beneath the water. They were ready to support the longest suspension span ever constructed. But the bridge was still far from complete. The next crisis was not underwater. It was inside the cables. By May of 1877, the towers were standing. Workers began spinning the four main cables. Each cable contained thousands of individual steel wires bundled together under immense tension. The entire suspended bridge would depend on them. If the cables failed, the bridge would fall. That made the steel supplier one of the most important contractors on the project. His name was J. Lloyd Hay. Hay had secured the contract to provide the bridge's wire, but he supplied material that failed to meet the required standard. Inspected batches were allegedly replaced with weaker and more brittle wire before delivery. By the time Washington Roebling's engineers discovered the fraud, hundreds of tons of inferior wire had already been incorporated into the main cables. It could not simply be removed. Once the wires had been carried across the river, tensioned, compressed, and wrapped together, they became part of the permanent structure. Removing them would have required dismantling a major section of the bridge. Roebling made the only practical decision available. He left the defective wire in place, then ordered approximately 150 additional wires to be added to each cable. The bridge had been designed with a large safety margin. The extra wire compensated for the weaker material. The defective steel remains inside the Brooklyn Bridge today. Once the main cables were secured, workers began constructing the roadway. One section at a time, the suspended structure took shape above the river. Large steel trusses extended along the bridge. Cross-bracing connected them into a rigid, triangulated framework. This system helped prevent the twisting and instability that had destroyed earlier suspension bridges. By early 1883, the structural skeleton was complete. A vast lattice of steel now stretched between the towers. The bridge was designed to carry pedestrians, carriages, and trains. A raised promenade ran through the center. Roadways and railway tracks occupied the levels below. After more than 13 years of construction, the Brooklyn Bridge was finally ready to open. On May 24, 1883, the New York and Brooklyn Bridge officially opened to the public. Construction had taken 13 years and cost approximately $15.5 million. It would not officially become known as the Brooklyn Bridge until 1915. An estimated 150,000 people crossed it on opening day. President Chester A. Arthur attended the ceremony and walked across the bridge. That evening, fireworks illuminated the East River. Newspapers called it the eighth wonder of the world. But only 6 days later, celebration turned into disaster. Approximately 20,000 people crowded onto the narrow wooden promenade. A woman stumbled on a staircase. Someone screamed. A rumor spread that the bridge was collapsing. Panic moved through the crowd. People at the rear pushed forward. Those near the front tried to move back. Within moments, people were crushed against the railings and trampled on the stairs. 12 people were killed. Dozens more were seriously injured. Public confidence collapsed overnight. People who had celebrated the bridge only days earlier now feared it was a death trap. Then came one of the most famous publicity stunts in American history. The showman P.T. Barnum had previously asked to parade his circus animals across the bridge. The city had refused. But after the deadly panic, the bridge needed a dramatic demonstration of its strength. On May 17, 1884, Barnum led 21 elephants across the Brooklyn Bridge. At the rear was Jumbo, one of the most famous elephants in the world. The message was simple. If the bridge could safely carry a herd of elephants, it could safely carry ordinary people. The stunt worked. Public fear faded. The crowds returned. But familiarity does not mean understanding. The Brooklyn Bridge still contains secrets. Inside the enormous stone anchorages at each end of the bridge are vaulted chambers. For decades, the city rented some of these spaces to merchants. Wine and champagne were stored inside because the thick stone walls kept the chambers cool and stable. Hidden inside the foundations of the Brooklyn Bridge were working wine cellars. The vaults even contained inscriptions praising wine, music, and celebration. Then, in 2006, workers exploring one of the hidden chambers discovered something unexpected: a forgotten Cold War fallout shelter. Inside were water containers, medical supplies, blankets, and boxes of emergency crackers. Many of the supplies were dated 1957 and 1962. Years associated with some of the most dangerous moments of the Cold War. For decades, the Brooklyn Bridge had concealed an emergency nuclear shelter inside its stone structure. Most of New York had no idea it existed. Now return to where the story began. The Brooklyn Bridge was the impossible engineering project of its age. It was built using technology that had barely been tested. Its foundations were excavated by men working inside pressurized chambers beneath a river. But it also connected two cities, changed the development of New York, and transformed the future of bridge engineering. More than 140 years later, it is still standing. So, here's the question. What is the impossible engineering challenge of our own age? And who will be brave enough to enter the unknown, take the risks, and build it? For more documentaries about extraordinary engineering, hidden disasters, and the people who changed the world, subscribe to the channel. And we will see you in the next video.